Point in any direction. Up, down, left, right, toward Orion, toward the Southern Cross. It doesn't matter. Now imagine traveling in that direction. Not walking, not flying, not even at the speed of light, but instantly, magically, covering 1 billion light years with each heartbeat. 1 billion light years per second. Galaxies blur past you like snowflakes in a blizzard. Galaxy clusters, superclusters. The largest structures in the universe become streaks of light, then vanish behind you. Keep going. How long until you hit something? A wall, an edge, a boundary, a sign that says, "Universe ends here, thanks for visiting." The answer is, you never do. You travel for 1 billion years at 1 billion light years per second. You've covered a distance so vast that the number of zeros would fill this entire video. And there's still more universe ahead of you. Still more galaxies. Still more space. You travel for 1 trillion years. A quadrillion. Numbers lose meaning. Time loses meaning. And still, the universe continues. You pass more galaxies than there are grains of sand on Earth. More stars than there are atoms in your body. More space than any mind can comprehend. And you keep going. Is it infinite? Does it go on forever? Or is there something stranger going on? Something that defies our intuition about space, about edges, about what it means for something to end? This is one of the deepest questions humans have ever asked. Philosophers have pondered it for millennia. Scientists have probed it with telescopes and mathematics. And the answers we've found are stranger than anything our ancestors imagined. Tonight, we're going to chase that question as far as human knowledge can take us. We're going to discover that where does the universe end is actually several different questions, each with a different answer. And we're going to confront the possibility that the universe might be so large, so strange, so fundamentally alien to our everyday experience, that the question itself might not have the kind of answer we're looking for. This is going to get weird. Stay with me. Let's start with what we can actually see. Right now, as you watch this video, light is entering your eyes. That light left your screen a few nanoseconds ago, travelled across the room and landed on your retina. Simple enough. But light takes time to travel, and that simple fact has profound implications for how we see the universe. The light from the sun took 8 minutes to reach you. If the sun disappeared right now, poof, gone, you wouldn't know for 8 minutes. You'd see the sun shining, feel its warmth, have no clue that it was already gone. The light from the nearest star, Proxima Centauri, took 4 years to reach you. When you look at Proxima Centauri in the night sky, you're seeing it as it was 4 years ago, not as it is now, 4 years ago. The light from the Andromeda Galaxy took 2.5 million years. 2.5 million years. When you look at Andromeda, you're seeing it as it was when our ancestors were just learning to walk upright. The photons hitting your eye right now left Andromeda before humans existed. Before Homo sapiens, before Homo erectus, before the genus Homo itself. You're looking at ancient history. You're seeing the past, frozen in light. This is the fundamental strangeness of astronomy. We never see the universe as it is. We only see it as it was. Looking out into space is looking back in time. The farther away something is, the older the light we receive from it. Look at a galaxy 1 billion light years away, and you're seeing it as it was 1 billion years ago. Look at the most distant galaxies we can detect, and you're seeing them as they were over 13 billion years ago, close to the beginning of the universe itself. We are time travelers. Our telescopes are time machines. Every observation of the distant universe is an observation of the ancient past. And here's where it gets interesting. The universe is about 13.8 billion years old. That means light has had 13.8 billion years to travel towards us. You might think that means we can see 13.8 billion light years in every direction. But you'd be wrong. Because while that light was travelling towards us, the universe was expanding. The space between galaxies was stretching. The starting point of that light, the place where it originated, has been moving away from us the whole time. So that light that's been travelling for 13.8 billion years, it didn't start 13.8 billion light years away. It started much closer. But by now, the place it came from is about 46 billion light years away. This is the radius of the observable universe, 46 billion light years. Let me make sure you feel this number. 46 billion light years. Light, the fastest thing in the universe, would take 46 billion years to cross that distance. But the universe is only 13.8 billion years old. How is that possible? Because of expansion. While light travels towards us, space itself is stretching. The light is running on a treadmill that's speeding up. By the time the light arrives, the treadmill has carried its starting point much farther away than the light actually travelled. It's like walking towards a friend on an escalator that's moving away from you. You walk 10 meters, but when you arrive, you've moved 20 meters relative to where your friend started. The observable universe is a sphere centered on you, on Earth specifically, with a radius of 46 billion light years. Everything inside that sphere has had time to send light to us since the Big Bang. Everything outside that sphere hasn't. Not because there's nothing there, but because the light hasn't reached us yet. Think about that. There are galaxies out there, real galaxies, with real stars, possibly with real planets and real life, whose light has been travelling toward us since the moment they formed, and that light still hasn't arrived. It won't arrive for billions more years. Maybe it will never arrive if the expansion carries them away faster than their light can reach us. Those galaxies exist, but we can't see them. We might never see them. The edge of the observable universe isn't a wall or a boundary. It's a horizon, like the horizon you see when you stand on the beach. There's more ocean beyond the horizon. You just can't see it from where you're standing. But the cosmic horizon is weirder than the ocean horizon. The ocean horizon is just a limitation of geometry. You could sail beyond it. The cosmic horizon is a limitation of physics. You can't travel beyond it. You can't see beyond it. You can't know what's beyond it. Not because it's forbidden, because there hasn't been enough time. So our first answer to where does the universe end is the observable universe ends 46 billion light years away in every direction. That's as far as we can see. That's our cosmic horizon. But that's not where the universe ends. That's just where our vision ends. What's beyond the cosmic horizon? Almost certainly, more universe. The cosmic microwave background, the oldest light we can see, the afterglow of the Big Bang, tells us that the universe was extremely uniform in its early moments. The same temperature everywhere to 1 part in 100,000. The same density, the same physics. This uniformity is remarkable. It means that whatever region of space became our observable universe was part of a much larger, homogeneous whole. The Big Bang didn't happen at one point in space. It happened everywhere, simultaneously, across all of space. And there's no reason to think that uniformity stops at our horizon. The universe almost certainly continues beyond what we can see, with more galaxies, more stars, more planets, stretching out, how far? Here's where things get tricky. We don't know. We can't know in a direct sense. Information from beyond the cosmic horizon can't reach us. We're limited by the speed of light and the age of the universe. Anything beyond 46 billion light-years is, in a very real sense, unknowable. We can observe the cosmic microwave background and see that the universe was uniform. We can measure the curvature of space and find it's flat. We can run simulations and see what kinds of initial conditions produce universes like ours. But we can't see beyond the horizon. We can't receive signals from there. We can't send probes. Whatever is out there, it's beyond the reach of any experiment we could ever perform. But we can make educated guesses, and those guesses are both humbling and mind-bending. Let me tell you about inflation. In the first tiny fraction of a second after the Big Bang, we're talking about 10 to the power of minus 36 seconds, a number so small it's basically zero. The universe underwent a period of incredibly rapid expansion. Space itself expanded faster than the speed of light, doubling in size again and again and again, perhaps 60 to 100 times or more. Let me put that in perspective. If something doubles 60 times, it grows by a factor of about 10 to the 18th power, a billion billion. If something doubles 100 times, it grows by a factor of about 10 to the 30th power, a million trillion trillion. And each of these doublings took an unimaginably small fraction of a second. The entire inflation period lasted maybe 10 to the power of minus 32 seconds. In that time, a region smaller than an atom expanded to larger than the observable universe is today. This is called cosmic inflation. It's one of the leading theories in cosmology, supported by observations of the cosmic microwave background. It explains why the universe is so uniform, why it's so flat, why we don't see certain exotic particles that other theories predict. But here's the thing about inflation. It's almost too good at expanding. The theory doesn't just predict that the universe expanded a lot. It predicts that the universe expanded by an absolutely absurd amount. And it has a terrifying implication for the size of the universe. During inflation, the universe expanded by a factor of at least 10 to the power of 26. That's a 1 followed by 26 zeros. Some models suggest it expanded by 10 to the power of 50, or 10 to the power of 100, or even more. The observable universe, everything we can see, is about 93 billion light-years across. That's already incomprehensibly vast, but it might be a grain of sand on an infinite beach. If inflation expanded the universe by a factor of 10 to the power of 26, then the actual universe could be at least 10 to the power of 26 times larger than what we can see. That means for every galaxy in the observable universe, there might be 10 to the power of 26 galaxies we can't see. The observable universe contains about 200 billion galaxies. Multiply that by 10 to the power of 26, and you get a number so large that it has no meaning. A number larger than the number of atoms in the observable universe. A number that your brain literally cannot conceptualize. For every star we can observe, there might be more stars beyond our horizon than there are atoms in your body. More stars than there are grains of sand on every beach on Earth. More stars than there are seconds since the Big Bang. And that's the conservative estimate. Some inflationary models suggest the universe is not just unimaginably large, but actually infinite. Not very big infinite, actually, mathematically, endless infinite. Let me try to explain what that means. When mathematicians say something is infinite, they don't mean really, really big. They mean without limit. No matter how far you go, there's more. No matter how much you count, you never finish. The concept of all of it doesn't apply because there's always more. This is hard to grasp. Our intuitions rebel against it. Here's an example. Think of the natural numbers. 1, 2, 3, 4, and so on. How many are there? Infinitely many. There's no largest number. Whatever number you name, you can always add 1 to get a bigger number. But here's the strange part. The even numbers, 2, 4, 6, 8, are also infinite. And you might think there are fewer even numbers than natural numbers, since you're skipping every other one. But mathematically, they're the same infinity. You can pair every natural number with an even number, 1 with 2, 2 with 4, 3 with 6, and both lists go on forever. Infinity doesn't work like regular numbers. Half of infinity is still infinity. Infinity plus 1 is still infinity. Infinity minus 1,000,000 is still infinity. An infinite universe doesn't have an edge. It doesn't have a center. Every point is equivalent to every other point. You could travel forever and never reach a boundary, never see the same place twice, never run out of new territory to explore. This is hard to visualize because our brains evolved to handle finite things. We understand big, we understand far away. We don't really understand infinite. But the math works. General relativity, our best theory of space and time, allows for infinite universes. The equations don't care whether space goes on forever or wraps around. Both are valid solutions. The observations are consistent with an infinite universe. We measure the curvature of space and find it's flat or very close to flat. A flat universe, extending uniformly in all directions, would be infinite. We can't prove it's infinite, but we also can't prove it's finite. And if the universe is infinite, then where does it end has a simple answer. It doesn't. The universe doesn't end. It goes on forever. But that simple answer opens up strange implications. But let me tell you why this might not be the whole story. Even if the universe is infinite in the usual sense, infinite space filled with infinite galaxies, there's another way to think about endings. A more subtle way, a stranger way. Let me tell you about the shape of space. You probably think of space as a big empty box, 3 dimensions, length, width, height, extending forever in every direction. That's the intuitive picture. That's what Euclidean geometry describes. That's what seems obvious. But obvious isn't the same as true. General relativity, Einstein's theory of gravity, tells us that space doesn't have to be Euclidean. Space can be curved. And the curvature of space changes everything about how we think about edges and boundaries. What does it mean for space to be curved? How can emptiness have a shape? Think about it this way. Imagine you're an ant living on the surface of a balloon. You can only move on the surface. You have no concept of up or down away from the surface. Your entire universe is 2-dimensional. You think your universe is flat. When you walk in a small circle, everything seems normal. The angles of triangles add up to 180 degrees. Parallel lines stay parallel. Standard geometry. But if you walk in a really big circle, a circle that goes around the whole balloon, strange things happen. You end up back where you started without ever turning around. Parallel lines, if you extend them far enough, actually meet. The geometry breaks. Your balloon universe is curved. But the curvature is only visible on large scales. Locally, it looks flat. Now, is your balloon universe finite or infinite? It's finite. The surface of a balloon has a definite area. If you walked far enough, you'd eventually return to where you started. But does your balloon universe have an edge? No. There's no boundary, no wall, no "here be dragons" at the margins. You can walk forever without hitting anything. The surface curves back on itself. It's finite but unbounded. This is a key concept. Finite doesn't have to mean has an edge. Unbounded doesn't have to mean infinite. This is what a closed universe would be like in 3 dimensions. Finite in volume, but without edges. If you travelled far enough in a straight line, you'd eventually return to where you started. Not because you turned around, but because space itself curves back on itself. Is our universe like this? We've measured the curvature of space using the cosmic microwave background and the distribution of galaxies. We've analysed the pattern of temperature fluctuations in the oldest light in the universe. We've done the math, and as far as we can tell, the universe is flat, Euclidean, uncurved. But, as far as we can tell, has limits. Our measurements are precise, but not infinitely precise. The universe could be very slightly curved, so slightly that we can't detect it. A very large closed universe would look flat to us, the same way the Earth looks flat when you're standing on it. If the universe is closed but very large, then it's finite but unbounded. It has a definite volume, incredibly vast but finite, and it has no edge. You'd never reach a wall, you'd just keep going, eventually returning to where you started. How large would it have to be for us not to notice the curvature? At least 400 times larger than the observable universe. Maybe much larger than that. But there's another possibility. The universe could be open, curved the opposite way, like a saddle or a Pringle chip. An open universe is infinite. It goes on forever, and space actually accelerates away from you as you travel. In an open universe, the angles of triangles add up to less than 180 degrees, and parallel lines diverge. Or the universe could be flat, truly flat, not just apparently flat. A flat, infinite universe. Euclidean space extending forever, exactly as our intuition suggests. Right now, the data favours flat. But flat is the boundary between closed and open. It's the knife edge case. It's mathematically special. And it's suspicious, actually, that the universe appears to be so close to perfectly flat. Of all the possible curvatures, why this one? That's part of why physicists developed inflation theory. Inflation naturally drives the universe toward flatness. Whatever curvature existed before inflation gets stretched out, diluted, until the universe appears flat to any observer inside it. So, the universe might be finite but unbounded, closed. It might be infinite, flat, or open. We don't know which. And we might never know, because the answer might lie beyond our observable horizon. And there's another layer to this that I haven't mentioned yet, a deeper strangeness. Let me tell you about topology. Curvature is about the local shape of space, how space bends in any small region. Topology is about the global shape, how space connects to itself on large scales. These are different things. You can have flat space with non-trivial topology. You can have curved space with simple topology. The two properties are independent. Here's an example. Take a piece of paper. It's flat, zero curvature. Now roll it into a cylinder. Still flat. The intrinsic curvature hasn't changed. An ant walking on the paper wouldn't notice any difference in local geometry. Triangles still have angles that add up to 180 degrees. Parallel lines still stay parallel, locally. But the topology has changed. On the flat sheet, if you walk off one edge, you fall off. On the cylinder, if you walk far enough in one direction, you loop around and return to where you started. The cylinder is still flat, but it wraps around. Locally ordinary, globally strange. Now take the cylinder and bend it into a donut shape, a torus. Still flat intrinsically. The curvature you see from outside, the bend of the donut, isn't intrinsic curvature. An ant on the surface would measure everything as flat. But the topology is now even stranger. You can loop around in two different directions, around the hole and through the hole. Two independent ways to return to your starting point. Space could be like this. The universe could be flat, locally Euclidean, but have a non-trivial topology. It could wrap around on itself in ways that are invisible locally, but matter globally. If the universe is a three-dimensional torus, for example, then it's finite but unbounded, no edges. But if you travel far enough, you'd see the back of your own head. Light from your flashlight would eventually circumnavigate the universe and return to you. Imagine the implications. You look at a distant galaxy, then you look in a different direction and see the same galaxy. A different view of it, from a different angle, but the same galaxy. Because light from that galaxy has traveled all the way around the universe and reached you from multiple directions. In a wrapped universe, the night sky would contain multiple images of the same objects. Not just galaxies. Eventually, if you looked far enough, you might see multiple images of the sun, multiple images of Earth, maybe even multiple images of yourself from different moments in time, because the light took different paths of different lengths. Have we looked for this? Yes. We've searched for patterns in the cosmic microwave background that would indicate a small, wrapped universe. We've looked for matching circles, regions of the sky that should look identical if we're seeing the same piece of space from different directions. We haven't found them. This means that if the universe does wrap around, it's too large for us to detect the wrapping within our observable horizon. The wrapping scale is bigger than 46 billion light-years, bigger than the observable universe. But that doesn't mean the universe isn't wrapped. It just means we can't tell. So the topology question is unresolved. The universe might be simply connected, no wrapping, or multiply connected, wrapping in one or more directions. We don't know. This gives us yet another answer to where does the universe end? If the universe has non-trivial topology, it might be finite without having an edge. It ends in the sense of having a finite volume, but it doesn't end in the sense of having a boundary you could reach. The universe could have a size without having a border. But let me take you somewhere even stranger. So far, we've been talking about the universe as if it's one thing, One space, one time, one set of physical laws. What if that's wrong? Let me tell you about the multiverse. The term multiverse gets thrown around a lot, often in confusing ways. There are actually several different multiverse concepts, and they're not all the same. Let me walk you through the main ones. Level 1. The quilted multiverse. If the universe is infinite, truly infinite, then everything that can happen does happen somewhere. This sounds crazy. It sounds like mysticism. It sounds like something a stoner would say at 3 a.m. But it follows logically from infinity. Here's the argument. There are only so many ways to arrange particles in a region of space. The number is huge, but it's finite. In a region the size of the observable universe, there are perhaps 10 to the power of 122 possible configurations of matter and energy. Let me try to help you grasp that number. 10 to the power of 122 is already incomprehensible. It's a 1 followed by 122 zeros. But 10 to the power of 10 to the power of 122 is 10 raised to that power. It's a number with 122 digits. Writing it out would require more atoms than exist in the observable universe. But it's finite. There's a limit to the number of ways things can be arranged. If space is infinite, then there are infinitely many regions the size of the observable universe. Infinitely many patches of space, each 93 billion light-years across, each containing some configuration of matter and energy. And if there are infinitely many regions, but only finitely many configurations, then configurations must repeat. It's like rolling dice. A single die has 6 faces. Roll it once, you get 1 face. Roll it 1 trillion times, you'll get each face many times. Roll it infinitely many times, you'll get each face infinitely many times. The same logic applies to the universe. If space is infinite and configurations are finite, then every configuration occurs, not just once, infinitely many times. Somewhere out there, unimaginably far away, but real, there's another region that's identical to our observable universe. Same galaxies, same stars, same planets, same you, reading these same words, thinking these same thoughts. How far? Roughly 10 to the power of 122 meters. A distance so large that writing it out in full, even using atoms as digits, would require more atoms than exist in the observable universe. But if space is infinite, that distance exists. That place exists. You exist there, exactly as you are here. And there are other regions, even more of them, where things are almost identical. Where you made a different choice this morning. Where your parents never met. Where dinosaurs never went extinct. Where life never arose on Earth. Where Earth never formed. Every possible variation of history playing out somewhere in the infinite quilted multiverse. This is deeply unsettling. It means there's no such thing as uniqueness. Everything that can exist, exists. Every version of you, every version of history, every possibility made actual. It also means the concept of where does the universe end breaks down completely. In the quilted multiverse, the universe doesn't end. It repeats forever in infinite variations. This isn't speculation. This is a logical consequence of infinity plus physics. If you believe the universe is infinite and the laws of physics are the same everywhere, The quilted multiverse follows with mathematical certainty. Level 2. The inflationary multiverse. Remember inflation, the rapid expansion in the first moments after the Big Bang. Here's something strange about inflation. Once it starts, it's hard to stop. Inflation is driven by a field called the inflaton field. When this field has high energy, space expands exponentially. The higher the energy, the faster the expansion. Space doubles, doubles again, faster than anything else in physics. When the field decays to low energy, inflation ends, and you get a Big Bang, a hot, dense region that expands and cools into a universe like ours. The energy that was driving inflation converts into particles, radiation, matter. The universe we know begins. But here's the catch. The field doesn't decay everywhere at once. It decays in patches. Random quantum fluctuations cause the field to drop to low energy in some regions, triggering a Big Bang there. But in other regions, the field stays high, and inflation continues. Each patch where the field decays becomes a universe, a bubble of post-inflationary space, expanding and cooling, developing structure and complexity. Our observable universe is one such bubble. But between the patches, inflation continues. And because inflation is exponential, the inflating regions grow faster than the patches can eat into them. For every bubble that forms, the remaining inflating space grows larger than the space the bubble consumed. The result is eternal inflation, an infinite, ever-inflating background, constantly spawning new universes in bubble-like regions. Each bubble is a universe unto itself. Each might have different physical constants, different particles, different laws, depending on how the inflaton field decays in that region. Our observable universe is one bubble in this infinite foam. But there are infinitely many others, forever being born in the inflating void. These other universes aren't somewhere in our space. They're not at a certain distance, in a certain direction. They're in their own spaces, disconnected from ours. We can never reach them, never see them, never interact with them. They're separate realities, causally isolated from us forever. The inflating space between bubbles expands faster than light. Light from one bubble can never reach another. Information can never cross the gap. For all practical purposes, each bubble is its own universe, complete and self-contained. Where does the universe end? In the inflationary multiverse, our universe ends at the edge of our bubble. Beyond that edge is inflating space, space that's expanding exponentially, creating new bubbles, generating new universes. But the multiverse, the ensemble of all bubbles plus the eternally inflating background, might be infinite. It might never end. It might be the ultimate context in which our universe is just one of infinitely many islands. Is eternal inflation true? We don't know for certain. It's a consequence of many inflationary models, but not all of them. The evidence for inflation itself is strong. The cosmic microwave background shows patterns consistent with inflationary predictions. But eternal inflation is a step beyond, into territory we can't directly observe. If it's true, though, the question, where does the universe end, takes on a new meaning. Our universe ends where our bubble ends, but the multiverse goes on forever, spawning new universes eternally. Level 3. The Many Worlds Multiverse. This one comes from quantum mechanics. In quantum mechanics, particles exist in superposition, multiple states at once, until they're measured. An electron isn't at one place or another. It's in a combination of places, described by a wave function. When you measure a particle's position, you get one answer. But quantum mechanics describes the particle as being in all positions simultaneously before measurement. What happens to the other positions when you measure? The traditional answer: they disappear. The wave function collapses to a single outcome. The electron was spread out and now it's at one place. The other possibilities just evaporate. But this is strange. Why should measurement be special? What counts as a measurement? When exactly does the collapse happen? The collapse postulate is added to quantum mechanics somewhat awkwardly, without a clear mechanism. There's another interpretation, the many worlds interpretation. In many worlds, the wave function never collapses. Instead, the universe splits. When you measure a particle, you get one answer in this branch of reality. But other branches exist too, branches where you got different answers. The branches don't interact, can't communicate, but they're all equally real. Think about what this means. Every time a quantum event happens, and quantum events happen constantly, trillions of times per second, everywhere in the universe branches. An electron passes through a slit. In one branch, it goes left. In another, it goes right. Both branches are real. Both versions of the experiment continue. You make a decision. In one branch, you turn left. In another, you turn right. Both branches are real. Both versions of you continue. The number of branches is constantly multiplying. The tree of reality is expanding exponentially, forever. Infinitely many branches, infinitely many versions of history, infinitely many copies of you, making infinitely many choices. In this picture, the universe includes all branches, and it never ends. It keeps branching forever into an ever more complex tangle of realities. Is many worlds true? We don't know. It's one of several interpretations of quantum mechanics, and we can't experimentally distinguish between them. But some physicists think it's the most elegant interpretation, the one that takes the mathematics of quantum mechanics most seriously. If it's true, then asking, where does the universe end, becomes even stranger. The universe doesn't just extend infinitely in space, it extends infinitely in possibility. Every branch is real. Every outcome happens somewhere. Level 4. The mathematical multiverse. This is the most radical idea. Physicist Max Tegmark has proposed that every mathematically consistent structure exists as a physical reality somewhere. Let me explain what that means. Our universe is described by certain mathematical equations. General relativity describes gravity. Quantum mechanics describes particles. The Standard Model describes forces and fields. Together, these equations predict what happens in our universe with astonishing accuracy. But these aren't the only possible equations. Mathematicians have studied many other consistent mathematical structures, other geometries, other algebras, other systems of rules. Most of these don't describe our universe, but they're mathematically valid. They're internally consistent. They work as systems of rules. Tegmark's radical proposal is this: every one of these consistent mathematical structures exists as a physical reality somewhere. Not just could exist, actually exists, is real, has physical instantiation. This includes universes with different numbers of dimensions. universes where time works differently, universes where the rules of logic are subtly altered, universes with physics so alien that we couldn't begin to imagine what it's like to exist there. Every coherent mathematical system made manifest as reality. If this sounds crazy, consider that we already accept something similar on a smaller scale. We accept that the mathematical equations of physics are real in the sense that they correctly describe our universe. Tegmark is just taking this further. If mathematics describes reality, maybe mathematics is reality. Maybe physical existence is just what mathematics feels like from the inside. In this view, asking, why does our universe have these particular laws, has a simple answer. It doesn't have to. Every possible set of laws exists somewhere. We find ourselves in a universe with these laws because these are the laws that allow for beings like us. If this is true, then where does the universe end has a truly bizarre answer. The universe, or rather the ensemble of all universes, extends to the limits of mathematical possibility, which is to say, it doesn't end at all. Every conceivable reality exists, somewhere, somehow. This is speculative in the extreme. It might not be testable in principle. Many physicists consider it more philosophy than physics. But it shows you how far the question, where does the universe end, can be pushed. It shows you that the question might not have any boundary at all. Now, I should be clear. We don't know if any of these multiverse ideas are correct. The level 1 quilted multiverse follows logically from an infinite universe, which we haven't proven. The level 2 inflationary multiverse follows from eternal inflation, which is plausible but not confirmed. The level 3 many worlds interpretation is one of several interpretations of quantum mechanics, and we can't experimentally distinguish between them. The level 4 mathematical multiverse is highly speculative and maybe not even testable in principle. But these ideas show you how physicists think about the question, where does the universe end? They show you that the question might not have a simple answer, or might have many answers, depending on what you mean by universe and end. They show you that the universe might be even stranger, even larger, even more alien to our intuitions than we can possibly imagine. Let me bring this back to something more concrete. Forget the multiverse for a moment. Let's talk about something we can actually observe: the fate of the universe we live in. Even if we can't find the edge of space, there might be an end in time. The universe might not have a boundary, but it might have a destiny. What will happen to the universe in the far future? The answer depends on the mysterious substance called dark energy. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. We discovered this in 1998, one of the biggest surprises in the history of cosmology. Two teams were studying distant supernovae, trying to measure how fast the expansion was slowing down. They expected to find deceleration. Instead, they found acceleration. The universe isn't just expanding, it's expanding faster and faster. This discovery won the Nobel Prize in 2011. It revolutionized our understanding of cosmic evolution, and it painted a bleak picture of the future. We don't know what dark energy is. It might be a cosmological constant, a fixed property of space itself, an energy inherent to the vacuum. It might be a dynamic field that changes over time, sometimes called quintessence. It might be something we haven't thought of, something that doesn't fit into any current theory. Whatever it is, It makes up about 68% of the universe's total energy content, and it's pushing everything apart. If dark energy continues doing what it's doing, the future of the universe is bleak. Galaxies are receding from us. As the expansion accelerates, they recede faster. The ones that are already far away will move away faster and faster, never slowing down. Eventually, distant galaxies will be moving away from us faster than the speed of light. Wait, faster than light? Isn't that impossible? Objects can't move through space faster than light. That's one of the fundamental laws of physics. Nothing can outrace a photon. But space itself can expand at any rate. There's no speed limit on the expansion of space. Space isn't an object moving through some larger arena. It's the arena itself, stretching. And stretching can happen arbitrarily fast. If space between two galaxies expands fast enough, those galaxies will be moving apart faster than light. Not because either galaxy is breaking any rules, but because the space between them is growing faster than light can cross it. This is happening right now. There are galaxies we can currently see that are already receding faster than light. The light we see from them is old light, emitted before they cross that threshold. We're seeing them as they were in the past, not as they are now. And we'll never see them as they are in the future, because their future light will never reach us. As the universe expands, more and more galaxies will cross this threshold. They'll redshift into invisibility. Their light stretch to longer and longer wavelengths, dimmer and dimmer, until it's undetectable. They'll fade from our cosmic horizon and be gone forever. One by one, the lights will go out. Trillions of years from now, our local group of galaxies, the Milky Way, Andromeda, a few dozen smaller galaxies, will have merged into a single giant elliptical galaxy. Gravitationally bound together, unable to escape each other. A lonely island in an infinite sea. But everything beyond our local group will have vanished beyond the cosmic horizon. No other galaxies, no distant lights, just darkness in every direction. Astronomers in that distant future will look out at the universe and see nothing. No cosmic web, no great walls of galaxies, no evidence of the Big Bang except what their predecessors recorded. They will have no way of knowing that the universe ever contained more than their one galaxy. They'll develop astronomy and see only their own stars. They'll develop cosmology and have nothing to study but their own isolated island. The universe will look small to them, finite, comprehensible. And they'll be wrong. The universe will be vaster than ever, but all of it hidden, receded beyond the horizon, gone. And then, slowly, the stars will die. This is the part of the future that's hardest to grasp, not because it's conceptually difficult, but because the timescales are so long that they make a mockery of everything we understand about time. 100 billion years from now, about 7 times the current age of the universe, star formation will be essentially over. The gas that fuels star formation will be used up, dispersed into the void, unavailable. No new stars will be born. The existing stars will continue burning, but stars don't burn forever. The sun will die in about 5 billion years, swelling into a red giant that engulfs Mercury and Venus, before shedding its outer layers and collapsing into a white dwarf. A white dwarf is a stellar corpse, dense, hot, slowly cooling. No fusion, no energy generation, just a ball of degenerate matter, radiating away its stored heat. Most stars will end this way. Red dwarfs, the most common stars in the universe, will burn the longest. A red dwarf can sustain fusion for trillions of years. But even trillions of years isn't forever. Eventually, the last red dwarf will exhaust its hydrogen and fade into a white dwarf. 10 trillion years from now, give or take, the last star will die. After that, the universe will contain no fusion, no starlight, no warmth from stellar furnaces, just the cooling corpses of stars, white dwarfs, neutron stars, black holes, and the scattered debris of planetary systems drifting through the dark. Black holes will dominate. In the centers of every galaxy, supermassive black holes, millions or billions of solar masses, will reign over dead stellar populations. Stellar mass black holes, the remnants of massive stars, will wander through the void. Black holes might seem eternal. They're famous for being inescapable, inexorable, the ultimate endpoints of gravitational collapse. But even black holes aren't eternal. Hawking radiation, a quantum mechanical process, causes black holes to slowly evaporate. At the event horizon, where space-time curves most extremely, the quantum vacuum fluctuates. Particle-antiparticle pairs pop into existence, briefly, before annihilating. But at the horizon, sometimes one particle falls in and the other escapes. The escaping particle carries away energy. The black hole loses mass. This process is excruciatingly slow. A stellar mass black hole, say 10 times the mass of the Sun, takes about 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros. For comparison, the current age of the universe is about 10 to the power of 10 years. So a stellar mass black hole would take about 10 to the power of 57 times longer than the current age of the universe to evaporate. Supermassive black holes take even longer. A black hole with 1 billion solar masses would take about 10 to the power of 100 years to evaporate. 10 to the power of 100 years. That's a Google. A 1 followed by 100 zeros. A span of time so long that the current age of the universe, 13.8 billion years, is less than a rounding error. It's less than nothing. It's so small compared to a Google that it might as well be zero. But eventually, even the black holes are gone, evaporated into Hawking radiation, a faint mist of particles spreading into the ever-expanding void. What remains? What remains? This is the heat death of the universe, the final equilibrium, maximum entropy. The universe will be a void filled with a thin, cold soup of particles. Photons, electrons, positrons, neutrinos, drifting through space, almost never interacting, spreading thinner and thinner as space expands. The temperature will approach absolute zero, but never quite reach it. There will always be some faint background radiation, some residual heat, but it will be cold, unimaginably cold, colder than anything you can conceive. Nothing will happen. Not because time has stopped, time will continue, but because nothing interesting can happen. No temperature gradients to drive engines, no free energy to do work, no structures to decay. Just equilibrium, forever. Physicists call this state maximum entropy. Entropy is a measure of disorder, of randomness, of how spread out energy is. In a low entropy state, energy is concentrated and organized. In a high entropy state, energy is dispersed and uniform. The universe started in a remarkably low entropy state, concentrated, organized, full of potential. Over time, entropy increases. That's the second law of thermodynamics, one of the most fundamental laws of physics. Energy spreads out, gradients dissipate, order dissolves into chaos. Heat death is the end of that process. Maximum entropy. No more gradients, no more potential, nothing left to happen. Is this an ending? In a sense, yes. It's the end of structure, the end of change, the end of anything we would recognize as interesting. The universe becomes a cold, dark, empty expanse, thinning out forever. But space itself doesn't end. The expansion continues. The void keeps getting voidier. There's no wall, no boundary, no final destination, just dissipation, dilution, the slow fade into nothingness. The universe will still exist. It will just be boring. Unless dark energy changes. If dark energy is dynamic, if it can increase over time, then the future might be very different. There's a theoretical possibility called the Big Rip. If dark energy increases, the expansion of the universe will accelerate faster and faster. Not just galaxies receding from each other, everything flying apart. First, galaxy clusters will be torn apart. The gravitational bonds that hold clusters together will be overcome by the expansion of space. Then individual galaxies. The stars that orbit galactic centers will be flung outward as expansion overwhelms gravity. Then solar systems. The planets will be ripped away from their stars, Earth from the Sun, the Moon from Earth. Then planets themselves. The atoms that hold planets together will be overwhelmed. Worlds will disintegrate into clouds of atoms. Then atoms. The electrons will be torn from nuclei. Matter itself will come apart. Eventually, space will expand so fast that everything is ripped to shreds. The fabric of space itself might tear. Space-time might develop holes, discontinuities, singularities everywhere at once. When would this happen? It depends on the properties of dark energy. It could be hundreds of billions of years away, or it could be sooner. We don't know, because we don't know what dark energy is. In the Big Rip scenario, the universe has a definite ending, a moment when space itself breaks down, a true apocalypse, the end of everything, everywhere, all at once. But we have no evidence that this will happen. Current observations are consistent with constant dark energy, which leads to heat death, not the Big Rip. Most physicists think heat death is more likely, but we don't know for sure. The nature of dark energy is one of the biggest mysteries in physics, and the fate of the universe hangs on the answer. There's also the opposite possibility. Dark energy could decrease or even reverse. If gravity somehow overcomes dark energy in the far future, the expansion could slow, stop, and reverse. The universe would begin contracting. Galaxies would approach each other. Space would shrink. After billions of years of expansion, compression. After the void, the crush. Everything that spread apart would come back together. Eventually, everything would collapse into a single point, a big crunch, the mirror image of the Big Bang, the universe ending as it began, in a singularity, a point of infinite density where the laws of physics break down. Would that be the true end? Maybe. Or maybe the Big Crunch would trigger a new Big Bang, a cyclic universe, endlessly expanding and contracting, dying and being reborn. We have no evidence for this either. The observations don't support a reversal of expansion. But it's a theoretical possibility, a different kind of ending, or a different kind of non-ending. So when you ask, where does the universe end? The answer in time might be, in about 10 to the power of 100 years, in a cold, dark, empty nothing. Or maybe sooner, in a violent rip. Or maybe in a crunch that seeds a new beginning. We don't know, and we probably can't know, because the answer depends on the nature of dark energy. And dark energy remains one of the deepest mysteries in physics. Let me take you back to the question of space. We've talked about the observable universe, 46 billion light-years to the cosmic horizon. We've talked about the whole universe, possibly infinite, possibly finite but unbounded, possibly one bubble in an infinite multiverse. We've talked about the future, heat death, big rip, big crunch. But there's one more thing I want to tell you about. One more way to think about endings. Let me tell you about the edge of knowledge. There are things we might never know. Not because we're not smart enough, not because our technology isn't good enough, but because of fundamental limits written into the laws of physics. If the universe is infinite, we can never confirm that. We can only see our finite patch. The rest is beyond our horizon, beyond our reach. We can extrapolate, we can theorize, we can make educated guesses, but we can never observe. We can gather evidence that suggests infinity. For example, measurements showing the universe is flat, which would be consistent with infinite extent. But consistent with is not proof of. A very large finite universe would look the same. If other universes exist, other bubbles, other branches, other mathematical structures, we might never detect them. They might be fundamentally inaccessible. In the inflationary multiverse, other bubble universes are separated from us by eternally inflating space. We can't travel there. We can't see there. We can't even receive signals from there. They're causally disconnected from us, as disconnected as two events can be. In the many worlds multiverse, other branches are separated by quantum decoherence. They exist in some sense, but they don't interact with us. We can't verify them. We can't communicate with them. We can only infer their existence from the mathematics of quantum mechanics. If the universe has a non-trivial topology, if it wraps around in some complicated way, we might never discover it if the wrapping scale is larger than our horizon. We've looked for evidence of wrapping. We haven't found it. But that doesn't mean the universe isn't wrapped. It might just be wrapped on a scale too large for us to detect. And if that's the case, we'll never know the true topology of space. These aren't temporary limitations. They're not like we don't have powerful enough telescopes yet. They're fundamental. The speed of light, the age of the universe, the nature of cosmic horizons, these set absolute limits on what we can observe. Some questions might be unanswerable in principle. Is the universe infinite? We might never know. Are there other universes? We might never know. What is the topology of space? We might never know. What caused the Big Bang? We might never know. The singularity itself might be beyond the reach of physics. This is a strange kind of ending. Not a physical edge, but an epistemic one. The edge of what can be known. The universe might be knowable in principle. Every question might have an answer we could someday discover. Or it might not. Some truths might be forever hidden from us, not because they don't exist, but because we can never access them. In that case, where does the universe end might be a question without an answer. Not because the answer doesn't exist, but because we can never know it. Maybe that's the most honest answer to the question. The universe ends where knowledge ends. Beyond our cosmic horizon. Beyond our ability to measure and confirm. Beyond the reach of light and logic. There might be more out there. Almost certainly there is. But it's not ours. It's not accessible to us. It might as well not exist from our perspective. Is that a satisfying answer? Probably not. We want to know. We want to see the edge, touch the boundary, understand the whole thing. But the universe doesn't owe us satisfaction. The universe doesn't owe us comprehensibility. It is what it is, and we see what we see, and the gap between those might be unbridgeable. This is humbling. This is terrifying. This is also, strangely, beautiful. We are small creatures in a vast cosmos, asking questions about things immeasurably larger than ourselves. We can't answer all the questions. We can't know everything. But we can ask. We can wonder. We can reach toward the edge, even if we never arrive. That reaching, that wondering, might be the point. Not the destination, but the journey. Not the answer, but the question. Let me try to tie this together. Where does the universe end? Answer 1. The observable universe ends 46 billion light-years away. That's the cosmic horizon, the limit of what light has had time to reach us. Beyond that, we cannot see. Answer 2. The whole universe probably extends far beyond our horizon. It might be finite, but unbounded. A closed space that wraps around on itself. It might be infinite, endless space going on forever. We don't know which. Answer 3. If the universe is infinite, everything possible happens somewhere. There are copies of you, variations of Earth, alternate histories, all real, all unimaginably far away. Answer 4. There might be other universes, other bubbles in an eternally inflating multiverse, other branches of the quantum wave function, other mathematical structures made real. If so, the universe is just one of many, and the multiverse might have no end at all. Answer 5. In time, the universe will end in heat death, a cold, dark, empty void stretching forever, with nothing happening, nothing changing. Unless dark energy does something unexpected, in which case, all bets are off. Answer 6. The universe ends where knowledge ends. Some things might be forever beyond our ability to observe or confirm. The edge of the universe might be the edge of what we can know. None of these answers is entirely satisfying. They're all partial. They all have uncertainties. They all leave something out. But that's the nature of the question. Where does the universe end is not a question like, where does France end? A question with a definite, mappable answer. It's a question that pushes against the limits of human understanding. A question that reveals how strange and vast and alien the cosmos really is. Let me leave you with something to think about. You are here, on Earth, a small planet orbiting an ordinary star in an ordinary galaxy. That galaxy contains about 400 billion stars. The observable universe contains about 200 billion galaxies. That's something like 10 to the power of 24 stars in the observable universe. A trillion stars. And the observable universe might be a tiny fraction of the whole universe, a droplet in an ocean, a speck in an infinity. You are unimaginably small. Your life is unimaginably brief. The patch of space and time you occupy is less than a rounding error in the cosmic ledger. And yet, you are the universe looking at itself. You are atoms that have arranged themselves into a pattern that can ask, where do I end? You are the cosmos made conscious, wondering about its own edges. That's not nothing. That's remarkable. The universe might be infinite. It might have no edge, no boundary, no comprehensible shape. It might contain endless copies of you, endless variations, endless possibilities. Or it might be finite. It might have a shape we'll someday understand. It might be one of many, a bubble in a foam, a branch on a tree. Either way, you're part of it. Whatever the universe is, you're made of it. Whatever its extent, you're somewhere in it. Whatever its fate, you share it. Where does the universe end? Maybe the better question is, where does it begin? Because the universe begins wherever you are. It begins in your neurons, your breath, your heartbeat. It begins in the act of wandering. It begins here, now, in this moment, when a pattern of matter asks about the pattern of everything. The universe might have no edge, but it has a center. You. Not because you're special, but because you're here. Because you're asking. Because the universe is asking, through you. Where does the universe end? Look around. Look inside. Look at your hand, made of stars. The universe ends where you stop looking. And as long as you're looking, as long as you're wondering, as long as you're asking, it doesn't end at all. Let me take you deeper. I've told you about the observable universe. I've told you about inflation and infinite space. I've told you about multiverses and heat death. But I want to make sure you really feel the scale of what we're talking about. Because numbers like 46 billion light years and 10 to the 24th power stars are too big to mean anything. They slide off the brain like water off glass. Let me try again. A light year is about 9.5 trillion kilometers. To travel 1 light year at highway speed, say 100 kilometers per hour, would take about 11 million years. Just 1 light year. The nearest star is 4.2 light years away. At highway speed, 46 million years. The nearest large galaxy, Andromeda, is 2.5 million light years away. At highway speed, 27 trillion years. The Sun will have died, the Earth will have vaporized, the Milky Way and Andromeda will have merged and dispersed long before you'd arrive. And Andromeda is in our cosmic backyard. The most distant galaxies we can see are over 13 billion light years away. Their light has been traveling since before the Earth existed, before the Sun existed, before most of the stars in our galaxy existed. And they're within our observable universe. They're within the 46 billion light-year radius we can access. What's beyond that? If the universe is only 10 times larger than the observable portion, a conservative estimate, then the whole universe contains 1,000 times more volume than what we can see. 1,000 times more galaxies. 1,000 times more stars. If the universe is 10 to the power of 26 times larger, a plausible inflation-based estimate, then the whole universe contains 10 to the power of 78 times more volume than the observable universe. 10 to the power of 78. Let me try to help you feel that number. There are about 10 to the power of 80 atoms in the observable universe. So the whole universe might contain almost as many observable universe-sized regions as there are atoms in our observable universe. Each of those regions could be as rich and complex as everything we've ever seen or will ever see. Each could contain its own galaxies, its own planets, its own civilizations, its own beings asking, where does the universe end? And that's still assuming the universe is finite. If the universe is infinite, truly infinite, then it contains infinitely many observable universe-sized regions, infinitely many galaxies, infinitely many copies of Earth, infinitely many copies of you. Not a really big number. Infinite, without limit, beyond counting. This is what we're talking about. This is the scale of the question. Where does the universe end? It might not. Let me tell you about something called the cosmic web. On the largest scales, the universe is not uniform. Galaxies are not scattered randomly like dust in a sunbeam. They're organized into a vast network, a web of filaments and sheets surrounding huge empty voids. Imagine looking at the universe from the outside, if such a thing were possible. You'd see a structure like a three-dimensional spiderweb, or maybe like the neurons in a brain. Bright nodes connected by thin threads with dark voids between them. The filaments are made of dark matter and galaxies. They stretch for hundreds of millions of light years, thin threads of matter connecting denser regions. Where filaments intersect, there are dense clusters containing thousands of galaxies. These clusters are the largest gravitationally bound structures in the universe, the biggest things that can be called objects. The voids are almost empty, regions hundreds of millions of light years across, containing very few galaxies. They're not completely empty. There are some galaxies even in voids, lonely islands in a sea of nothing. But mostly, the voids are just that, void, empty, dark. The contrast is striking. In a cluster, you might find 10,000 galaxies packed into a region a few million light years across. In a void of similar size, you might find 10 galaxies, 1,000-fold difference in density. We've mapped this web to a degree. The Sloan Digital Sky Survey and other projects have catalogued millions of galaxies and traced the structure. Computer simulations have recreated the web, starting from tiny fluctuations in the early universe and watching gravity pull matter into filaments and clusters over billions of years. The simulations match reality remarkably well. We understand in broad strokes how the cosmic web formed. But the details are still being worked out, and the scale is still being revealed. The largest structures we've identified are staggering. The Hercules Corona Borealis Great Wall is about 10 billion light years across, roughly a tenth of the observable universe. The giant GRB ring is a ring-shaped structure about 5 billion light-years in diameter. The Sloan Great Wall stretches for 1.4 billion light-years. These structures are so large that they challenge our theories. They're almost too big to have formed in the time since the Big Bang. Gravity works slowly. For matter to have gathered into structures this large, it must have started clumping very early and continued clumping ever since. But even these structures are just pieces of the pattern. The cosmic web continues beyond them, and beyond our observable universe, the web presumably continues further. If the universe is infinite, the web goes on forever. Filaments connecting clusters, connecting superclusters, all the way out, without end. An infinite structure of infinite complexity. If the universe is finite, but very large, the web fills the entire volume, a three-dimensional pattern repeating and varying, filling space with its lacy structure, all the way to wherever space curves back on itself. Tracing the cosmic web to its edge, if it has an edge, would mean mapping a structure that dwarfs anything in human experience, dwarfs anything we can even conceptualize. The cosmic web is the universe's skeleton, and we've only seen a piece of one bone. Now let me tell you about the ultimate fate of structure. In the far future, 100 billion years from now, 1 trillion years, a quadrillion years, the cosmic web will dissolve. Galaxy clusters will merge. Gravitational interactions will eject some galaxies into the void, while others sink to the center. Eventually, each local group will collapse into a single mega-galaxy. But those mega-galaxies won't stay intact. Stars would escape through gravitational interactions. Over trillions of years, galaxies will evaporate, losing their stars to intergalactic space. The stars themselves will die. New stars won't form. The gas is used up, dispersed, unavailable. The universe will go dark. What remains will be the compact objects, white dwarfs cooling toward absolute zero, neutron stars spinning down, black holes slowly evaporating. On timescales of 10 to the power of 40 years, protons might decay. If they do, white dwarfs and neutron stars will dissolve into a thin soup of electrons, positrons, and photons. On timescales of 10 to the power of 67 years, stellar mass black holes evaporate. On timescales of 10 to the power of 100 years, supermassive black holes evaporate. After that, we don't know. Physics gets speculative. Maybe the false vacuum decays. Maybe space-time fluctuates. Maybe something genuinely new happens. But in the heat death scenario, after the black holes are gone, the universe is just particles, photons, leptons, drifting through an ever-expanding void. The temperature approaches absolute zero. The density approaches zero. Activity approaches zero. This is the end, in the sense of ending of structure. Not an edge in space, but a fade in time. The universe will still exist. Space will still be there, presumably, expanding. But there will be no galaxies, no stars, no planets, no life, no observers. Nothing to see the universe, nothing to wonder about it. The universe will continue, but it will be empty. Is that an ending? It's hard to say. If a universe exists but contains nothing interesting, does it matter that it exists? Maybe not. Maybe the meaningful universe, The universe that contains experience, structure, change, does have an end. In time, if not in space. But the physical universe, the mathematical structure, the space and time and energy, that might persist forever in some attenuated form. The universe might be eternal in its existence, but finite in its interest. Let me tell you about the anthropic landscape. This is the idea that many different physical laws are possible, and we find ourselves in a universe with laws that allow for our existence. Because if the laws didn't allow for our existence, we wouldn't be here to ask. The landscape refers to the vast number of possible universes predicted by string theory. String theory suggests that there are something like 10 to the power of 500 different configurations of extra dimensions and fields, each giving rise to different physical constants and particles. Most of these configurations would lead to universes that don't support life. No chemistry, no stable atoms, no stars, just chaos or stasis or nothingness. But some configurations, some tiny fraction, would allow for complexity, life, minds. And we necessarily find ourselves in one of those. If this is correct, then the universe, meaning the one we inhabit, is one possibility out of an inconceivably vast landscape. Most of the landscape is sterile. We're in a rare oasis. Where does the universe end in this picture? Our universe ends wherever our configuration of physical laws applies. It might be a bubble in a larger multiverse, where each bubble has different laws. The boundary between bubbles would be a kind of edge, not of space exactly, but of physics. What's across that boundary? A different universe, different rules, probably incompatible with our existence. You can't go there, not because it's far away, but because there operates under different rules than here. Your atoms wouldn't work there. Your chemistry wouldn't work. You wouldn't work. The edge of the universe might be the edge of the laws that make you possible. Let me bring this back to human meaning. We've covered a lot. Observable universe, infinite space, multiverse, heat death, anthropic landscape. But you're not an abstract entity trying to understand the universe. You're a person, living a life, caring about things. Does any of this matter? Paradoxically, I think the vastness of the universe makes things matter more, not less. If the universe were small and cozy, everything would be significant by default. But the universe is vast beyond comprehension. Most of it is empty, cold, and dead. In that context, this, here, is rare. This planet, this life, this moment. The fact that anything interesting exists at all is improbable and precious. You are a pocket of complexity in a universe trending towards simplicity. You are a brief eddy in a river flowing towards stillness. You are a temporary violation of the ordinary, which is emptiness and silence. The universe doesn't care about you. It's not the kind of thing that can care. But you can care about the universe. You can look up and ask where it ends. You can be the part of the cosmos that wonders about the rest. That's not nothing. That's everything. Where does the universe end? Maybe it ends where meaning ends, where there's no one to ask the question, where the last observer fades out and the cosmos continues, unseeing, unseen. But right now, meaning exists. You exist. The question exists. And as long as there's someone asking, the universe doesn't end. It begins, over and over, every time a mind opens its eyes. I've given you many answers tonight. 46 billion light years, the horizon of the observable. Possibly infinite, the extent of space. Finite but unbounded, if space curves back on itself. Multiverse, if our universe is one of many. Heat death, the end of structure in time. The edge of knowledge, where we cannot see or know. All of these are true, in some sense. All of them are incomplete. The universe is too big, too strange, too multifaceted for any single answer. It resists simplification. It defies summary. But maybe that's okay. Maybe the point isn't to get the final answer. Maybe the point is to keep asking. The question, where does the universe end, is not a problem to be solved. It's a direction to be explored. It's a frontier that recedes as you approach it. That can feel frustrating. We want answers. We want closure. But the universe offers something better. Mystery, depth, endless exploration. Where does the universe end? We don't know. We might never know. But we get to ask. We get to wonder. We get to journey toward the edge, even if we never arrive. And that journey is the meaning of the question. So keep looking up, keep asking, keep wondering. The universe is vast. The universe is strange. The universe might have no end. But it has you, and you're looking. That's how the universe knows itself. That's how it finds its own edges. Through you, through this moment, through the act of asking. The universe ends? Not while you're watching, not while you're asking, not while minds exist to contemplate it. The universe began 13.8 billion years ago in a moment of infinite density and temperature. It has been expanding ever since, cooling, clumping, complexifying. It made stars, it made galaxies, it made planets and oceans and life. It made you. And now you sit here, a collection of atoms that somehow learn to wonder about all the other atoms. A temporary pattern asking about the permanent whole. A finite being contemplating the infinite. That's the deepest answer I can give you. Where does the universe end? It ends where the wandering stops. And as long as you're wandering, as long as someone, somewhere, is looking up and asking, the universe has no end. Just edges, just horizons, just the next question waiting to be asked. Go ask it.